Our next speaker is Peter Kish from University of Vienna, recently graduated from the University of Warwick, as we can see from the picture. If it's from Warwick, I don't know.
No, that's my Oxford graduation.
Okay, that's your Oxford graduation. Sorry.
To make it pretty.
Right, but the floor is yours.
So yes, I'm Peter Kish from University of Vienna, and I'm presenting a paper which appeared last year at Fox. The title of which is Dynamic One Epsilon Approximate Matching Size in Truly Sublinear Baseline. But don't let this confuse you. This is a sublinear paper. It was just for branding purposes, I would say, that we made it sound dynamic. And this was done with my supervisor Cheyenne and Tejapal Sarnarak from the University of Michigan. And I was at Max Planck at the time. So it's the affiliation. That's why there are three of them. So what is the setting? We're working on the approximate maximum matching problem, where you're given some graph, not necessarily bipartite, and you want to find a large matching of this graph or extended. Obviously, has a lot of history. Mu of G will stand for the maximum matching size, and we're in the approximate regime. We will say that a matching is alpha approximate for some alpha greater than 1 if matching m size of n times alpha is greater than mu of G. So I think I even have some picture here. Right, that's the 3 approximate matching. So I will differentiate two versions. The search version of the problem is where we actually look for the matching itself. And we can relax this to be a value version where we are just interested in the matching size estimate, which is defined to be alpha approximate the same way with respect to the maximum matching size. So throughout the presentation, for sake of simplicity, assume that the graph is very dense. Usually for matching problems, this is the hard instance. And also assume that the maximum matching size is large, say epsilon times n. There are technical tools which allow you to make this assumption, or otherwise it becomes, anyways, I'm not going to get into it, let's just make this assumption. So we will focus on two settings. The first one is the sublinear setting. Here our goal is to estimate the maximum matching size of the graph. But we want to be in polynomially sublinear with respect to the number of edges of the graph, and let's say n squared in this setting. Now, we define alpha approximation analogously, as I said, for our matching size estimates. Now we are polynomially sublinear in the input size. So it's a good question, how do we even access the graph? Because you don't really have time to reorder your adjacency list into a convenient format. So there are two main models people usually consider. One is the adjacency matrix query model, where you can query whether a particular edge exists between two vertices, or the adjacency list query model, where you can query the ith neighbor per vertex. In this presentation, think of the adjacency matrix model. This result we didn't extend to the list model. It will extend, I think. Most results usually extend into both of them, and they have slightly different trade-offs in terms of epsilon. The second setting where we'll talk about is the dynamic setting into the value version, where you're given a dynamic graph which undergoes edge updates. And your goal is to maintain a good approximation to the maximum matching size as the updates occur. Something like this. And your objective is to minimize the update time, the time you spend updating the output, and think of it as like amortized average update time throughout this presentation for simplicity. But all of these results can be extended, so it's worst case update time, meaning that they hold after each specific update. So why these two models in specific? I claim that from the perspective of the matching problem, there's a very simple connection between them. Say we have an alpha approximate sublinear algorithm, which runs in time roughly n to the 1 plus delta. I claim that there is a simple alpha plus epsilon approximate dynamic algorithm, which, runs in static time n to the 1 plus delta. And there's a dynamic algorithm which runs in time n to the delta update time. So how does this work? Well, at time 0, you just calculate an alpha approximate matching size estimate in n to the 1 plus delta time. You wait for roughly n updates, and recall we assume that the matching size is roughly n. Throughout these updates, your matching size estimate is roughly correct, and you just repeat. Simple as that. And then the update time works out to be n to the delta. So here I do want to mention that this assumption that the matching size is large can be guaranteed with existing results in literature with vertex parsification. So I'm not going to get into that, but that can be guaranteed for the dynamic set. So what are the existing results on this problem? The dynamic version is extensively studied, even though I can only think of one application of it, but it is very popular and I like it as well. And this is only results up until last year. But really the results kind of look like this. There is a hardness bound based on well-accepted conjectures that you can't really go below n update time for an exact solution. So everybody tries to do approximate. In the polylogarithmic update time regime, which is kind of the ideal one, what you would be aiming for, we can get down to 2. There's an interesting point at 3/2 approximation where you can get root n update time, and for 1 plus epsilon, you can only get n. And I will later, and n approximation, 1 plus epsilon approximation and update time can be done by recomputing just every epsilon and updates. But that's kind of the trivial. Those results only improve some polynomial factors on that. Right, so very recently there's a hardness band for 1 plus. Okay, sorry, I was reading the code. Very recently there's a hardness band for 1 plus epsilon approximation, but it's not reliant on well-accepted hardness conjecture and requires epsilon to be sub-constant. So yeah, it's a bit specific.
Sorry, Peter, can I quickly ask you what is the well-accepted conjecture?
I think you can do that from SET, you can do it from OMB, there are like 4 different papers. They get different polynomials. The best one is going to be n, and I don't recall which conjecture it is using. Right. So this is when we actually want to maintain the edges of the dynamic matching. So if we just want to maintain size estimates, you can actually do a bit better. There were some papers in 23 Soda, one of them by us, where it showed that you can get below 2 for polylog update time. And the other paper also showed that you can get below 3/2 in root and update time. So it already appears that in the dynamic setting, if you're only interested in matching size estimate, it's a bit easier. Might be a bit surprising, right? So this talk is about sublinear algorithms. So what are the results on that? That should be a B, sorry. So there's a paper from Fox 21, which showed that you can get 2 approximation in O tilde n time in the sublinear regime. And that is time optimal in the sense that it's easy to show that O tilde n is a lower band for any constant approximation to the maximum matching size. And afterwards, there was a Soda paper which showed that you go a bit above n, like n to the 1 plus epsilon, and you can get 199 approximation. More recently, there were 2 stock papers which show that you can get to 3/2 approximation if you are close to n squared, like n to the 2 minus poly epsilon. But there's nothing for 1 plus epsilon. So it's an interesting question how close you can get in both settings. 1 plus epsilon, there's no polynomial improvement over the trivial. Right. In terms of hardness for the sublinear regime, there's an interesting band which shows that n to the 1.2 is needed to be 3/2 approximation. And more recently, after this work, there's a lower band for 1 plus epsilon approximation, which shows that you need at least n to the 2 minus a function of epsilon time. So if you're getting close to 1 plus epsilon, you can't do n root 10, 1 plus epsilon approximation or something. Right, so what is the main result I'm presenting here? The main result is that in the adjacency matrix query model, you can get to 1 plus epsilon approximate matching size estimate in less than n squared time. So what I mean by this is that you can return a matching size estimate, which is epsilon n away from the maximum matching size. This additive slack is necessary for adjacency matrix queries, so this is essentially an optimal approximation in the sublinear regime. And the running time is going to be some n to the 2 minus a function of epsilon, where that function of epsilon is hiding a very, very tiny factor. So I would say that this is more of a theoretical result than anything else. So where does this fit on this picture? It just goes over there. So it's the first non-trivial result for arbitrarily tight approximations. And because of this more recent lower bound, which shows that n to the 2 minus another function of epsilon is necessary, this result is now known to be tight up until what that epsilon dependency is, because I think the lower bound is linear in epsilon and ours is very bad in epsilon, so there's some wiggle room, but you have to be very close to this. So recall this reduction, where we said if you can do n to the 1 plus delta sublinear, you can do n to the delta dynamic. Just black box substituting into this reduction, we get a sublinear in n update time dynamic algorithm, which maintains a 1 plus epsilon approximation to the maximum matching size. Works against adaptive adversaries and has worst case update time. These are terms for people who work with dynamic algorithms, but not that important at this point. Unlike the sublinear algorithm, you can make this algorithm to have an update time sublinear in root m. And it's an important thing to note that if you just rebuild every epsilon mu of g updates in the dynamic setting, you will get an algorithm with about n update time. So it's n update time is trivial in the for the 1 plus epsilon regime dynamic volume search version, where you actually want to maintain the edges. So in both of these models, this is the first algorithm beating the trivial approach for arbitrary tight. So it fits somewhere over there. So one thing to note is that I mentioned Liu's hardness bound for 1 plus epsilon approximation. As I mentioned, it doesn't rely on OMV or something like that. It relies on more specific conjecture, but also it requires epsilon to be sub-constant. And our update time is not sub n if epsilon is sub-constant. So unfortunately, this does not prove a strong separation between search and value version dynamic algorithms, which would have been very interesting. So the next talk I'll talk about the actual algorithm. And when I'm talking about it here, just about time complexity or time, it's all about query complexity. How many edges you need to reveal. All of the operations we do need to do will be roughly linear with respect to the number of edges we examine. So only just think about how many edges of the graph we had to see to get this estimate. So what would be a naive idea for approximating the maximum matching size of the graph sampling, right? What you bump into is that if you just do some random sampling and you would want to learn about the graph through just crude random sampling, the dense regions will dominate your sample, but they not necessarily dominate the maximum matching in the graph, if you have something like this. And in fact, there is a lower bound, which says that you cannot get any constant approximation with polynomially less than linear number of edge samples. So this approach, unfortunately, doesn't work at all. Okay. So it's a more general approach, and what is the approach we are following? And as far as I'm aware, every sublinear matching algorithm, but I might be incorrect on that one, is that we choose a static algorithm, a suitable one, and I'll define what I mean by suitable soon. It has better some ideal properties. It has, say, small parallel depth and very local, very randomized. We sample some polynomial vertices, and we check whether our algorithm matches these vertices, or how many of them it matches. We just calculate the solution locally, and then we extrapolate the ratio of matched vertices to the whole graph. Obviously, we will incur some slack, and this is where the necessary additive slack is appearing for the adjacency matrix model, but it will be a good estimate of the maximum matching size. So, okay, why is it not jumping? So, really the goal for for sublinear matching is more about locally computable algorithms. That is, you want, for a specific algorithm, you want to find an oracle which can efficiently tell you whether a specific vertex is matched, and for most purposes, we also need the matching edge in order to get a good estimate. And of course, you want to do this without accessing the majority of the edges of the graph. Right. So just to give an intention, I'll look at the previous result, which is a very elegant result, and it's time optimal from POX21, where this algorithm is just random ordered greedy matching, which is locally computed. So what is random ordered greedy matching? You just assign a random ordering to the vertices. You can think of it as assigning them a random value between 0, 1 and going in increasing order. And you just add any edge to your, you assign the values to the edges, and you just add any edge to your matching if it doesn't contradict any of the others. So for this input, this would be the matching you construct. And surprisingly enough, these algorithms admit you can query the output at a given vertex very, very efficiently. And this is because the randomized construction of the algorithm doesn't require you to search the whole input space. So for example, if you're interested in this middle edge, then we can completely ignore all edges which came after that edge in the random order, right? Because they do not affect its matching status. And based on this, we can decide kind of a recursive query structure which only requires for maximal matching just about n queries to return the match status of one single edge or vertex. Sorry, vertex, not for a single edge, it doesn't work for edge. Right. So this is just for intuition. We really want to have these recursive queries which somehow work out to be sublinear. I would say magically. This paper gives you 2 approximations roughly until that time. It's a very good read. So our goal is to find some algorithm which allows for such an efficient local computation. So we need to construct some oracle which can tell the matching status under some matching, and this matching is defined by the definition of the algorithm, the edges of the graph we reveal, and the random bits we choose, like here. Of course, we're not given them, and we were talking about a lot of these oracles, and just think of these oracles which have some running time and return for some particular vertex, that is whether it's matched under a particular matching and what its matching edge. So first, I have to talk about a suitable algorithm, which is 1 plus epsilon approximate and admits such an oracle. Our algorithm is McGregor's semi-streaming algorithm for 1 plus epsilon approximate matching. We don't really rely on the semi-streaming property at all. And in fact, you could replace this with a bunch of other algorithms. It's just the one we chose for convenience. So I will do some matching basics, algorithmic basics here, most of you will be familiar with. So this algorithm relies on augmenting path elimination. So what is an augmenting path? Say this purple matching is a matching we have calculated, or a starting matching like a greedy one, and let M star be a maximum matching, which we're not aware of course. And the union will construct this max degree 2 subgraph. And at some points they will match, at some points they will form a cycle, at some points they will form an even length path, but at other points they will form an odd length path. And each of these odd length paths can be used to extend the matching size by 1, if I would bind them, of course. This is what the standard historical matching algorithms all use. And since each odd length path can extend the matching size just by 1, if the number of paths is just upper bands, is exactly the difference. Number of odd length paths is exactly the difference between our matching size and the optimum. And if they're all long, that kind of implies that we are close to being a perfect matching. And there's a very specific well-known theorem for this, that if they are roughly 1 over epsilon long, then we are roughly 1 plus epsilon approximate. So what is the idea behind McGregor's algorithm, like many standard matching algorithms, is that you repeatedly try to find a constant fraction of some constant length augmenting paths. You repeat this a constant number of times, you will argue that for every length up until say 1 plus epsilon, there are only very, very few of them left, and then you make an argument that you are close to being optimal. I'm being very hand-wavy on purpose because these details will not be very important for us. So how to imagine such a step where you're actually finding augmenting paths? This will be important. Let's say that you start with some alpha approximate matching. The purple one, M, think of it as a greedy matching initially, which is well known to be 2 approximate. And we'll fix some length k, which is roughly at most 1 over epsilon, and we will be looking for k long augmenting paths, obviously k is an odd value, with respect to our current matching. Right. And once we have found the constant fraction of k long augmenting paths in a graph, we can use them to improve this alpha, sorry, that should be a minus, apologies, improve this alpha by a teeny tiny bit. And we will do that repeatedly, and this algorithm in particular does this a bunch of times. There are actually ones which do this in polynomial rounds, but from the trade-offs we get with this framework, it doesn't quite make a difference, because the other trade-offs are so bad already. So let's just look at 5 augmenting paths. We will first, so a purple matching is what we have, a red matching is, say, a maximum matching in this graph. We will first randomly put the vertices of the graph into 6 layers, really representing the potential augmenting paths. It will look something like this. This is very optimistic, of course. But regardless, a small fraction, an exponentially small fraction, depending on k, of augmenting paths will survive this brute partitioning in the sense that they will start in the leftmost layer and they just go till the right. So we'll start with the free vertex in the leftmost layer and then with the free vertex in the rightmost layer. So let's just focus on this. And of course, here we are being very hand-wavy with constants because this step already throws away like the majority of augmenting paths. And let's just try to find a constant fraction of the surviving augmenting paths. We start from the free nodes on the left, and we calculate a constant approximate matching to the nodes in the first layer. Now, we choose a constant delta, which will depend on k and epsilon, and we say that if we found the matching which is at least k times the size of number of free nodes, delta of this constant, the size of the free nodes, we say that this was successful. We have managed to start a lot of augmenting paths, and we continue. And then we continue, say, to the third layer, and we want to continue these augmenting paths. Okay, so now in the third layer, we do the same thing. We look for a constant approximate matching between the third and the fourth layer. We found that it was large enough. We said we were successful. Now, we will run into some problems. We now go into the fifth layer vertices of the paths we have found. Of course, the purple vertices we know, so that is not something we're looking for. And now we want to calculate a constant approximate matching between the fifth layer and the sixth layer. And that would finish our augmenting paths. But oh no, it could be that we get stuck. Like on this picture, we don't really know anything about the structure of these augmenting paths. This is a very brute force process. In this case, we just bend the vertices we got stuck at, since we know that you cannot finish paths from those vertices. They're kind of bad ends, and we just backtrack. Now, the intuition is that delta is so tiny, like this expansion rate is so tiny, that whenever we bend vertices, the majority of the vertices bend will be kind of bad nodes from which we can't finish. Like all of them will be bad nodes from which we can't finish, sorry. And they will just eliminate very, very tiny fraction of augmenting paths because delta is said to be so strict. I will say it this way. So here a lot comes down to these constant parameters being selected to be tiny, tiny. And we backtrack, and now from the third to the fourth layer, we again try to find a continuation of our augmenting prefixes of paths. We go to the fifth layer, and from the fifth to sixth, we actually manage to finish these paths. And now we augment the purple matching and repeat. And we do this a constant number of times. The exact constants, as I mentioned, are not very important. Just keep in mind that this happens a constant number of times. So for this particular algorithm, delta will be some k to the minus k, and there will be some, we find some k to the minus k fraction of augmenting paths. There will be a constant number of these augmenting phases where we are looking for paths. And we will find a constant and a huge constant number of matchings, approximate matchings like the green, yellow, and orange one or brown one throughout this process. And that's what you should keep in mind. There's a slight comment that the backtracking step doesn't introduce a lot of extra steps because in each backtrack we will ban a constant fraction of vertices. So in each of these phases, the backtracking will also happen a constant number of times.
Sorry, question. How is that different from like the blocking flow algorithm that you will be running for the constant steps?
It's not different.
It's that.
Like, there are many different variations of this. I'm not sure which one you're referring to. The importance of this particular algorithm was that it's semi-streaming and constant number of passes, because previously they had log factors, but this is back in 2005. So since then, there have been algorithms which get down to poly passes. Like, this can be done in smarter ways. I will define a very specific property of this algorithm, which we will be using though. So let's just think of what this algorithm needs to do in a single step. In a single step, it does one very specific thing. It just needs to find a constant approximate matching in a vertex-induced subgraph of the graph, and it doesn't need to do anything else. So for example, when we got the first matching, the green one, our vertex-induced subgraph is the yellow nodes in the third layer, that is the nodes to which we already have found an augmenting path prefix, and the free nodes in the fourth, and the endpoints of the purple matching in the fourth layer. So those are not yet free nodes, those are matching nodes, but yes. So what the definition of this vertex-induced subgraph depends on two things. One is all the previous matchings computed, right? That gives the structure, that defines the structure what we have found so far, and also the randomization of the layers we have chosen. Right, so this is a very specific property of this algorithm, and our sublinear framework can implement any static algorithm which just looks for vertex-induced subgraphs, which depend on these, where the subgraphs we're focusing on depend on these kind of, just the previous matchings. So let's think about this in a sublinear regime. Of course, in the sublinear regime, we will not be able to find any of these maximal matchings. You can show that finding a constant approximate matching in a sublinear regime is impossible. That's not hard to show. Unless the graph is regular or something very strongly is true. So what's going to be a problem here? Well, the randomization of the layers is not going to be a problem, because each vertex is put into layers at most a constant number of times. This is just order epsilon n work. So the randomization of the layers is something we'll be able to always find. The problem is that we will not be able to find the majority of the edges in these constant approximate matchings. And hence, we will not be able to identify the majority of these vertex-induced subgraphs, right? And the question is, can we get away with only the identifying little n vertices in these vertex-induced subgraphs? Like, this is my question. So in order to kind of answer this in a black box way, I will introduce an alternative problem, and I will show how it handles this whole construction intuitively in a black box way. On paper, it's quite messy, but it's roughly the same thing. And it follows the ideas of a previous paper from Stock 23. I will define an alternative problem now. Let's say you have a bipartite graph. Which I call the hidden matching problem, but since then I've heard that it means something else in another context, so don't confuse it with that. There is some hidden set A of vertices in this graph, which will be a vertex-induced matching, right, from the other algorithm. We know that this hidden set has a reasonably large matching inside of it. For some constant, it's like n times epsilon, so it has an interesting matching inside of it. And we have an oracle which can tell membership in A in roughly n to the 1 plus epsilon time. So what does this mean? We can query a lot of vertices membership in A, but we cannot query all of them. We can only query less than n to the 1 minus epsilon if we want to remain in the sublinear regime. So we'll not be able to identify A, obviously, would make anything we want to do trivial. And our goal is to construct a matching oracle which returns match status in a constant approximate matching inside of A. We want to do this such that we spend sublinear time constructing this oracle. And once we have constructed, it runs in roughly the same time as A's oracle does. It's just the epsilon is blowing up there. Does this make sense? Right. Okay, so this is a problem we for a long time believed to be impossible and wanted to prove that it's hard. So O of MA takes a vertex and tells whether it is matched under this matching inside of MA and tells the matched edge, if it's matched.
So there is a matching that OMFX, which is the MA.
Well, it doesn't complete it explicitly. So whenever we'll talk about matching oracle, its results have to be consistent, right? So if you ask, otherwise the whole extrapolating to the whole graph doesn't make sense. So all of these oracles need to be consistent if you query different nodes. So there is a fixed matching based on our random bits. There's a fixed MA, but we don't explicitly know it. And we don't even calculate all the random bits necessary for it. Which, yeah, this does have to be carefully defined, and it is in the paper, right? So how do we do this magical step? This is not primarily our idea, so we don't came novelty for it. Let's set K to be roughly n to the 2 epsilon. And just uniform sample K sets of edges from the graph of size n to the 2 minus 3 epsilon. Point being is that the total sampling we did is n to the 2 minus epsilon. Right, so we got a lot of these random samples, look something like that. And then we calculate greedy matchings, just random order greedy matchings in each of these sets we have calculated that will return us some matchings which look like that. Okay, this is our starting point. There will be 3 cases. Case 1 is the easy case, I would call it. When we got lucky, when one of these matchings we have explicitly sampled is indeed constant approximate inside of A. That's probably the easiest case, which looks something like this. This we can easily detect because we can just sample a small number of vertices from A and check whether they are matched under any of the matchings we have found. Like this is easy to detect. And in this case, the oracle we are constructing only needs to tell membership inside of this matching restricted to A. So this is probably the luckiest we can get. Right, now there's the case I would call the tricky one, when we didn't get so lucky. So let's fix MA star to be a maximum matching inside of A. Looks something like that. This case will be that one of the matchings we have found doesn't match both endpoints of a constant fraction of MA star. So this was a long sentence. So what does it mean? That say this red matching just for quite a bit of edges doesn't match both endpoints of MA star. So why is this good for us at all? So that's the edge we are focusing on here. Consider the complement graph of this matching. So the vertex-induced not the complement graph, the vertex-induced subgraph of the unmatched nodes onto this red matching. Those guys. I claim that this will have small maximum degree. And why is that? Well, intuitively, since this red matching was made out of a large sample, almost n squared in size, if any of these unmatched nodes would have a lot of edges running to other unmatched nodes under the red matching, we would have hit that set. Right? So it's reasonable to expect, of course you can prove it formally, that this will have roughly n to the 3 epsilon maximum degree. And here I will say that there are black box results for telling telling match status for constant approximate matchings with low query complexity if the degree is small. Even for 1 plus epsilon approximation, you can do that. And then we just run those oracles in the complement of this matching, which ignored both endpoints of a lot of MA star edges, in combination with the membership oracle with A. Right. So what is the last case we have? Well, we're not in the easy case. That is, all of the matchings ignore the majority. So all of the matchings we have just randomly calculated are not really inside of A, like they have one endpoint outside and one in maybe. But not only that, but that they all appear to match at least one endpoint of the majority of the black edges. So they look kind of like this. So they cannot be used really easily to find any black edge here. So in this case, we will recurse. We will do the following. So if you look at the union of these matchings we calculated, each endpoint of MA star has large degree inside of it. Because for every, not each endpoint, but like majority, the average degree of black edge endpoints is large in this union. Because these matchings we calculate kind of expand out of A and they're incident on MA star endpoints. So the idea is that we just sample some sublinear number of vertices inside of A. We can do this just by random sampling vertices in the whole graph and querying their match status under A, which for a sublinear number of vertices we can afford, say those red ones. And we just band their neighbors in the union of all of these matchings we have calculated. And because they have large degree inside of these matchings, because we are not in the easy or the tricky case, this will be a constant fraction of the vertices of outside of A. So somehow magically we have actually identified a large part of the complement of A in sublinear time, even though we only have a slow query access to A. And now we just recurse. Does this make sense? Right. Okay. So just intuitively have to imagine how does this create a sublinear algorithm, this hidden matching lemma we have calculated. Let's just look at this augmenting phase we previously had. Recall that the matching oracle to the purple matching, say, runs in time n to the 1 plus epsilon. We are up until some point in McGregor's algorithm. The randomizations of the layers we know explicitly because that takes small time to calculate. Then our hidden set will just be the free neighbors of the free nodes in L1 and the endpoints of the purple edges in L2, who have an endpoint in L3 as well. And we just construct an oracle to this green matching with the hidden matching lemma we had. Because it has all the appropriate inputs. It has a query oracle which to the hidden set which runs in sublinear time, right? And it's just a vertex-induced matching. And we just repeat. And every time we just construct a new oracle, which needs to call a constant number of previous oracles, which all run in time roughly n to the 1 plus epsilon. These will all be just oracles running in time n to the 1 plus epsilon. We use the hidden matching lemma, which does some sampling, but it's less than n square sampling it does, and it outputs another oracle which runs in time roughly 1 to the n to the 1 plus epsilon, and we do this until the end of McGregor's algorithm. Right. So what takeaway I would like you to have from this talk is that we can get arbitrarily close to maximum matching size in sublinear time. As we talked with others, this was something people disputed after the hardness band for better than 3/2 approximation appeared. So that's kind of an interesting thing. Because matching in general is something a lot of algorithms use as a black box, it already has some applications in shoveling salesperson and earth movers distance, which is nice. And the other thing is that this reduction I mentioned between dynamic and sublinear algorithms, previously it was not really written down, but I think it was known because of the vertex sparsification techniques existing, which ensure that the maximum matching size is large, so this whole framework makes sense. But previously, dynamic matching algorithms had update times better than sublinear algorithms. So this was the first instance when in a black box way, you could just yield a dynamic algorithm which beats the state of the art. So in general, this is a direction worthwhile to examine. That's a takeaway. And I would name 2 open problems to be exciting. I think in this regime, the most interesting problem is whether you can beat 2 approximation in roughly n time. Do note that in n for any constant approximation, you need omega n time. So that's kind of time optimal. I mean, of course, I mean O tilde n, so whatever other factors you need to hide, but that's the interesting one. And if you recall, this is how the dynamic update times work with respect to approximation, how that graph looks like. And this is how the sublinear looks like. And the dynamic actually has here a trade-off. But there are points here which I didn't draw, and there's also that point at root n. But the dynamic also has a point just here, which the sublinear does. So it kind of has the intuition that they should be the same. There should also be a trade-off here. Because at 3/2, everything jumps up to close to n squared, and that's kind of unsatisfactory. Like from 3/2 to 1 plus epsilon, the epsilon dependency is different, but you can do roughly the same, and this feels a bit bad. So the other question I would have is whether you can do a trade-off curve which exists for dynamic. We didn't write it down, but we can actually put something roughly here. So there are certain algorithms which have which do not have this flavor that they are slightly below n squared depending on epsilon and be to approximation. There's certainly other points in here, but I'm more interested in looking for a very general, an algorithm which matches all of these points. Because for matching, there is indeed an algorithm which matches all of these points with a unified framework. So it's the same thing as this for sublinear matching. That would be interesting, right? Anyways. Right, okay.
Right, thank you very much, Peter. More questions in the room? The lunch may not be ready yet.
Well, I can have a question.
You have a question?
You mentioned that the MacBaker's algorithm is just a placeholder,
Yes, yes.
but your whole, like, the things that you explained, it's very much dependent on how the MacBaker's algorithm works.
So I'll explain what I mean by placeholder if I, sorry. I made too many slides. So any algorithm will work as long as they repeatedly look for constant approximate matchings in vertex-induced subgraphs. And that membership in that vertex-induced subgraph just depends on membership in previous matchings and maybe some other computation which you can do in sublinear time. And then you can substitute in any algorithm. And we know there are such algorithms which actually run in poly-epsilon iteration. Multiplicative weight updates, for example. But that's restricted to bipartite graphs. But there are even ones for general graphs which do that. But the problem is that even if you would substitute in something which has poly rounds instead of exponential rounds, hidden matching lemma requires you to half epsilon every time. So you will not get an n to the 2 minus poly epsilon running time. We thought about it. You can improve on that 1 minus epsilon to the 1 minus epsilon to the 2 to the whatever, but like it would be interesting to make it poly, but we don't know how to do it even for bipartite graphs or MWU, and these techniques are a bit faster and simpler than for general graphs, because this all extends to general graphs as well, instantly. So yeah, this is what we need, is this vertex-induced subgraph, constant approximate matching magic is all it relies on. There are a bunch of other
At the
things.
end of the U, we're talking about this, the recent papers and Jiva and
There are many variants of MWU which work, but then there is another algorithm by Tarch and someone, I forgot the name, which 1 over epsilon square, semi-streaming, bipartite matching, 1 plus epsilon approximation. That's very simple, and it also does constant approximate matchings in each round in the same manner. So that's probably even simpler. And there's just 1 over epsilon squared, there's not even a log factor. Yeah, it's important that there's no log factor, so it has to be constant, right? Because we build a very deep structure. We will build a structure which is as deep as this thing. Right, so this is what I meant by it being a placeholder.
Thank you. More questions? I think, does it look, do we have any questions? All right, well, let's thank the speaker again.